Okay, so in this video I'm going to do an example of using Green's theorem, where instead of computing this line integral, which isn't that bad, you need to make a few trig substitutions, but instead of doing it like that, I'm going to do it as a double integral over this region D. Okay, but first, maybe I shouldn't have said that I was going to use Green's theorem instead of actually computing the line integral, because I am going to compute the line integral just to show you how much easier it is in some cases. So I don't particularly like this form of Green's theorem, or I don't like this form of like line integrals. I like it sort of like this. It makes more intuitive sense to me like this. But anyway, it was given to us like this. So alright, so let's parameterize this this circle here. So we have the positive orientation, which means that like if you walk around the curve, the region is on your left side. Okay, so that means that we can parameterize it like this. By the way, I'm going to try to make this video 10 minutes long, so I'm going to try to speed through it really quick. Okay, now let's compute dx and dy. So in this case, dx is going to be -2 sine theta and d theta, and dy is going to be 2 cos theta d theta. Okay, so basically, when the line integral is given to you in this form like this, where you have, this is going to make the video take longer, but usually like the vector field is given to you like this. And the way that I like it, you dot the vector field with your parameterization of the curve here. But when it's given to you like this, that guy right there is P, this guy here is Q. Okay? And basically when you have your parameterization, you just plug in all your values for x and y and for dx and dy. So, and you can see that theta goes from 0 to 2 pi, because it's this closed loop here. So I'm going to rewrite this line integral as the integral from 0 to 2 pi of theta. Okay, so here I'm going to use the fact that sine squared of something equals 1 minus cos of 2 of those things over 2. Okay, so here we have sine squared squared, so I'm going to make this substitution for that term. And then for this guy here, I'm going to use the fact that cos squared of something is equal to 1 plus cos 2 of those things. Here I have cos squared squared, so I'm going to make this substitution. Sorry, that's really messy. Okay, like I said, I'm trying to just go through this quickly because I want to actually use Green's theorem. Okay, but I'm just doing it like this to show you that, this isn't particularly hard, but you do have to make a couple of trig substitutions. And you'll see that when I actually use Green's theorem, when I compute the double integral over this region, it's actually really easy. It takes like 2 lines. Okay, so I'm going to write this in right quick. Okay, when you work this out, a few of the terms here cancel, like the 2 cos 2 thetas cancel, and you end up with this guy here. Okay, so I skipped a step there. When you square these guys out, you're going to end up with a term like this, cos squared 2 theta. Okay, and you're going to have one from here, and you're going to have, you're going to have one from here, and you're going to have one from here. So you end up with this thing here. Okay, so again, I make this substitution here as well. So I use the cos squared equals 1 plus cos 2 times the argument over 2 here, and I also have to use it again here. So I have one substitution for this, 2 substitutions for this, and the third substitution is right here. Okay, so when you work this out, you just have basically integral from 0 to 2 pi. Okay, so I guess this would be 8 divided by 2 is 4, and then 4 times 3 is 12, so I guess I could have a -12 right there instead of all this stuff here. Okay, so you'll see so I guess that would just be a 1. So from this term here, you can see that you have minus 24 pi, and then this is just, you're basically integrating coast between 0 and 2 pi. Okay, so hopefully you can quickly not waste your time with that and see that that's just going to be 0 there. So here's your final answer. Okay, sorry I skipped a lot of steps there. So let's see how we can simplify things using Green's theorem. Okay, so Green's theorem says that this line integral is going to be equal to some double integral. Okay, so like I said, this guy here is p, this guy here is q. So the formula for this here is, oh, sorry, I said q and wrote p, and then I wrote p again. So the formula for this here is partial q with respect to x, take away partial p with respect to y dA. Okay, so when we compute those partial derivatives, we end up with minus 3x squared minus 3y squared dA. Okay, so we can factor out the 3, and then we have the integral dA. Now, this integral is, I guess it would be sort of tricky if you did it just like that, but to simplify things, I'm going to use polar coordinates. So I'm going to make my substitution here that x squared plus y squared equals r squared, and I'm going to say that dA is going to equal to r dr d theta. Okay. Hopefully you know how to do polar coordinates. I hope you do, because that will make your life a lot easier in a lot of different cases. So now this integral is going to simplify to just this. Okay, when I make that substitution for r squared for this, and r dr d theta here, you can see that I end up with this r cubed term. And then when we integrate with respect to r first, you know, r is going to go from 0 to 2 here, so that's r. And then theta is going to go from 0 all the way around to 2 theta. Okay, so when we integrate with respect to theta, we're going to go from 0 to 2 theta. So now if you integrate this, you have negative 3. I'll do the inner integral first. So you have 1 over 4 r to the 4. Okay, so when you evaluate this this thing here from 0 to 2 like this, you end up with just 4. You know, so I guess that would just be negative 12. When you integrate this thing right here, you're just going to end up with 2 pi, multiply that by negative 12, end up with negative 24 pi, which is the same thing that we had up here. Okay, so I sort of made this longer than it had to be down here because I didn't want to lose you by skipping too many steps. But hopefully you can see that it actually simplified things quite a bit. Here we had to make 3 trig substitutions. You know, and they can get a lot more trickier than just this basic trig identity. But nonetheless, we had to make 3 trig substitutions. Down here, you know, I guess the hardest thing we had to do was to evaluate this double integral in polar coordinates here, which is pretty easy, and I would highly recommend you get used to doing that, because it will simplify your life greatly. Okay, so I don't know how long that was, but hopefully it was 10 minutes. Thanks a lot for watching.